Hello everyone, welcome back. In our previous video, we understood about the AVL tree concepts in a depth. And in this video, we'll cover the implementation for those concepts for insertion and deletion operation. We will cover how the node structure changes based on the implementation and what is meant by height of the node. And then we'll cover the insertion and deletion implementation code for AVL tree. So let's start. Generally, the node structure have left and right pointer, which basically points to left and right child of the node, and it contains the key, which represents the data in the node. But for AVL tree implementation, we'll add one more property, which is height, which represents the height of that node. So our node class will look like this, which will have one more property called height, and new node is initially added, will have height 1 as a default value. Now let's understand what is meant by height for each node. So height of the node in a tree is the number of nodes on the longest path from that node to the leaf, right? So generally there are two ways to count this path. First is counting nodes, which is the definition mentioned here. It means that the total number of nodes on the longest path, including that node itself till the leaf node. And the leaf node has a height of 1 as a, which we saw in a previous slide also, the default rate. So we basically check the number of nodes on that longest path. And the second way is counting the edges. So instead of checking the number of nodes on a longest path, we check the number of edges. That is the alternative definition. And in this case, the leaf node height is considered as a 0. Both of them can be used, but for our AVL tree implementation, we will use this counting nodes definition. So initially, the leaf node basically have a height 1. And the height for 40 is calculated basically the longest path from 40 to leaf is actually both the paths from 40 to 30 and 40 to 50 have same number of nodes 1 1 plus 1 for the 40 because we consider that node itself for which we are calculating the height. So 1 plus 1 2. For 60, the longest path is either 60 40 30 or 60 40 50, which contains 2 nodes, and 2 plus 1 for that node, 3. 3 is the height. So basically the formula is to calculate the height of the node, we do 1 plus 1 is for that node for which we are calculating the height plus maximum of height of the left subtree, comma, height of the right subtree. So whichever the maximum is there, we take it because we need to check the longest path plus 1. That is the height of that node. So in AVL tree implementation, these are the common functions we will use, like height function where it just returns the property height for that node. If it is null, then we just return 0. Get balance method to check the balance. We know that how we check the balance, basically height of the left subtree minus height of the right subtree. And if it is null, we just return 0. And this is just a max function to check the maximum out of these two numbers. Let's understand the AVL tree implementation for insertion. So this is our standard binary search tree insert method, where basically if we want to add a new key, which is less than the current node value, then we go on to the left side of that node recursively. And if the new key is greater than the current node, then we go on to the right side of that node recursively. And when we find the empty spot, we create a new node with the new key and return. We added this extra code here where we are updating the height of the node based on the formula which we discussed in previous slide. And then we check the balance. Balance is basically height of left subtree minus height of right subtree. And if suppose tree is balanced, then we just return the node as it is. And if the subtree is unbalanced, where node is root, then we basically check what type of imbalance it is. And based on the imbalance, we perform the specific rotation logic and return the new node or new root of that subtree. So let's understand with the example. Let's say we want to insert 50, 40, 30. Then the standard binary search tree insert function will be get called with null because initially the tree is empty. So 50 will be created as a new node and it is a root of the new tree with height 1. So it will be written from here. Now 40 we want to insert. So as I mentioned, in a standard binary search to insert, new key is less than, so it will go on to the left side. Otherwise, it will go on to the right side. Now 50 dot left is null. So here it will create a new node with value 40, and it will return where the previous insert function here. So 50 dot left, it will add reference of 40. And then it will come here, basically uh, update the height of 50, which is 1 plus 1, which is 2, based on this formula. And then balance of the node 50 is height of left subtree, my 1 minus height of right subtree 0, 1 minus 0, 1. So it is balanced. So insert 30. Insert function will be called recursively till we find the empty spot. So we will create the node 30. It will return basically to the previous function call. It will return here because 30 was less than 40. That's why the insert was called from here. So 40 dot left is now will have the reference of 30. So 30 became the left child of 40. The height of the 40 is updated to 2 and it is balanced. So it will return 40 node reference to the previous. Here it will come and update the height of the node 50, which is 3. Now the balance of the node 50 is 2, which is unbalanced. Now it will basically check what type of imbalance it is. So balance is greater than 1. It means the left side is heavy. But if the left side is heavy, on the left subtree, which side it is added? So now key, which we added is 30. It is less than node dot left dot key. Why node dot left dot key? Because balance is greater than 2 for this 50 node. So left side is 80. That's why we need to check the left side, node dot left. So 30 is less than 40. That's why it got added to the left side of 40. So it is left imbalance. So Z is 50. Y is node dot left, Z dot left, because it is a left heavy tree based on balance. So it is left imbalance, and we can easily fix it using right rotation. So this function call. So this is the right rotation logic, and we know the right rotation steps. First step is that basically the left child of Z becomes new root, and Z becomes the right child of that new root. Y dot right is equal to Z, and then Z dot left. If suppose 40 had any right child, then it would have become the left child of 50 for maintaining the binary search tree property. But 40 doesn't have any, it did not have any right child. So that's why there is nothing changed. And then we update the height of Z and Y to make sure that it is updated because the structure of the tree changed. Height is 1 for Z and height became 2 for 40. And the new root, which is Y, which is this 40, Z dot left was 40, which we had stored. It will be returned as a new root for that subtree. So it will be returned 40 here, and from there it will be returned. So the new root of the tree is 40. So this is how the right rotation logic works. Let's understand the another example where basically this is our existing tree. We want to insert 50 in it. Insert function will be called with root of the tree 30, 50 is the new key. So 50 is greater than 30, so it will go on to the right side recursively. 40, 50 is greater than 40, so it will again go to the right side. Now right side of 40 is null, so it found the empty spot. It created the node 50 and it returned where? The previous insert function. So node is 40. 40 dot right is the reference of 50. So 50 became right child of 40. It will update the height of 40. So height of the 40 became 2. Now the balance of 40 is 0 minus 1, which is minus 1. It is fine. So it will return the node 40 reference from here directly. It will not go into this if condition. Now it will come here. Now the height of the node 30 will become 3. The balance of the node 30 is 0 minus 2 is minus 2. So it is right here. So balance is less than minus. So it is because of the right subtree is heavy. But on the right subtree, where is 50 added? 50 is greater than 30 dot right. So 50 is greater than 40. So it got added to the right side of right subtree. So it is right right. So it is right right imbalance. So for that we need to do left rotation. So this is the left rotation logic. We know that for left rotation logic, left rotation at Z, which is 30 node, right? So we know that for left rotation, what we do in a left rotation, the right child of Z becomes new root and Z becomes the left child of Y, the new root. And if suppose Y had any left child, it would have become the right child of Z here. And then we update the height of Z and Y because tree structure changed. So this is the new height and it will return the Y, which is basically the new root. The right child of Z, it was right child of Z, right? So we are returning that as a reference because it became the new root of that subtree. Where it will return? It will return here. So from there, the new root of that tree, 40 became the new root of that tree. So this is how the left rotation logic is implemented, right? So this is the implementation of left rotation. Now, if you understand one more example to cover this left right. So let's say this is our existing tree where we will insert 40. Now 40 is less than 60, so it will go on to the left side recursively. Again left side. Now 40 is greater than 30, so it will go on to the right side of 30. It found the empty spot, created the new node, return to previous. So node dot right, node is 30, 30 dot right is the reference of 40. So 40 became the right child of 30. Now it will update the height of 30. Balance of 30, this subtree with 30 as a root is fine. 0 minus 1 minus 1. So it will return the reference of node 30 as it is. It came to node 50 here, then updated the height of 50. So which become 3. Now the balance of node 50 is the left subtree height is 2 minus 0, which is 2. So it is unbalanced. Now balance is greater than 1. It means it is unbalanced because of the left side heavy. But the new key, which is 40, got added to the right side of that left subtree. This tree is unbalanced because of the heavy left subtree, but the new key is added to the right side of that left subtree. That's why it is left, right. So we will do left rotation onto the Y first. As we know, we need to do double rotation. So left rotation logic we already saw. What we do in left rotation? The right child of the impacted, basically this one, we are calling onto the node dot left, right? Because we need to do left rotation here first. So we are doing node dot left. So left rotation will be performed, and we know the left rotation logic, which we also saw in previous slide, right? The right child of the 30 becomes the new root, and 30 becomes the left child of uh, 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 30 becomes the left child of new root. And we update the height also. So now it will return back where it will return here. So now 50 dot left is now contains the reference of node 40 because after left rotation the structure changed. Now it will do right rotation. We did the left rotation at Y, then which is node dot left. Y is nothing but the taller child of Z, right? So which was left side. So that's why we did node dot left in the left rotation. Now we will do right rotation at that node itself, which is the root of that unbalanced subtree, node 50. So right rotation, this is the right rotation logic, which we already know. In a right rotation, the left child of the Z becomes new root and Z becomes the right child of that new root. And if root had any right child, it would have become the left child of previous root. And then we updated the height of the tree Z and Y, which we, because the structure of the tree changed. Now for this subtree, the root became 40. So we are returning that new root. Right? Y is nothing but the Z dot left. 50 dot left was 40, right? So we are returning that 40 as a reference. Where we are returning here. Now it will be written, the reference of 40 will be written from here, where it will be written to the previous insert function. So 60 dot left will now contain the reference of 40, which we can see here. And now the tree is balanced. So this is how the left and right double rotation works. Now let's understand the AVL tree implementation for deletion. So one thing to remember or keep in mind that the rotation logic for insertion and deletion is same. So we don't need to cover left rotation, right rotation, logic again for deletion. So we'll understand the deletion concept, the implementation with one example only. So this is the standard delete method for binary search tree, where we try to find the key which we want to delete. We go to the left side if the key is less than the current node. If greater than current node, then we go to the right side. And here is the, once you find the key, if the key have one child or no child, then we handle like this. And if key have with two children, then what we do, basically we check the in order successor and then replace that node with the in order successor. That is how we do the binary search tree division for a node with two children. Right. So this is the min value node. It basically gives us the in order successor for the node which we are deleting. And then what we do, we then call the root dot write equal to delete node root dot write temp key. Why we are doing this? See, we swap the values. Now we need to delete that, start from that in order successor, so that we will come from bottom up and balance the tree properly. Right? We need to balance the tree because of deletion. So that's why we call delete node from there. And let's understand with the example. So this balance node is nothing but the same logic where we update the height and then check the balance. And if it is balanced, then we return as it is. Otherwise, we perform the rotation based on the imbalance type and then return the change structure. See, the rotation logic, as I mentioned, right rotate, left rotate, that rotation logic is same in insertion and deletion. Only these if conditions are different. What is this if conditions? These are the conditions to check what type of imbalance it is. So in case of insertion, we were checking the balance and we were checking what is the insertion path. Basically, at what side that new node was added. Like checking the value of new node and checking it with the subtree value. But in deletion case, what we check the balance and we check which side is more basically heavy, which side of the subtree is more heavy, so that we understand whether it is left rotation or right rotation or left right or right left, right? So this logic of checking imbalance is different in deletion and insertion. That is the only difference. So let's say we have this tree, we want to delete 50. Delete node will be called with node 50 as the root of the tree, and key is 50 we want to delete. So it will go into the else condition. It will find the minimum because 50 has a two children. So it will come here. It will find the min value node. Min value node is in order successor. What is the in order successor for node for 50? It is 70, right? Because that is the number comes after 50. 20, 30, 50, 70, right? In order successor. So we got the 70 node in a 10 and we are doing the key exchange. We are not changing the reference. We are just basically swapping the values, right? And then what we do? We call the delete node again. Which is root dot write, which is 80, because we need to go till this point, right? And delete this and then come back till root to balance the whole tree. And because when we move this in order successor to the node where we deleted, the tree might have become unbalanced somewhere on the downside, right? We need to fix it. So we need to, that's why start from the from the place where in order successor was there. So what we do, we call delete node 80 and keep on checking for 50. So root dot right, because in order successor is greater, right? So that's why we go on to the right side. So 80, then comma 50, then basically it will call delete node with 50, comma 50. So now we got the key. So now 50 does not have any child. So it will basically root will become null, right? Root dot left is also null. Root dot right is also null. Root is basically node 50 here. So it will return null. Where it will return null? It will return null to the previous delete node 80. So we had come from here, right? 80 dot left will now store the null, right? So now it will basically try to balance the node for node 80. Now it will update the height of the node 80. So height of the node 80 is 3 only. But the balance is 0 minus 2 minus 1. So it is unbalanced. Which type of unbalance it is? Balance is less than minus 1. It means it is unbalanced because of the right heavy side. But, okay, right heavy side. But we know that we need to check right subtree whether it is left heavy or right heavy. That we check using this. So get balance root dot right. Why root dot right? Because balance is less than minus 1. So 80 is unbalanced because of the right heavy subtree. So what we do? Get balance root dot right. We check whether it is left heavy or right heavy. If this is left heavy, then it is right left. If this is right heavy, then it is right right. So now the balance is greater than 0. It means it is left heavy. So that's why it is right left case. Right left case. So in that case, what we do? Right rotate at y. We see basically the taller child of z, which is root dot right. We do the right rotate there. In right rotate, we just now saw the implementation, right? The left child of the node where we are performing the right rotation. Here we are performing the right rotation. So left child of y is 85. So that becomes the new root. And y becomes the right child of that new root, right? And then we update the height. Then once it is done, it will return basically the reference of 85. Where will we store? It will be stored into the 80 dot right because we changed the structure here, right? Previously 80 dot right was 90. Now 80 dot right is 85. Then we do the left rotation at root, which is 80. Right rotation, left rotation. It is right left case. So we'll do the left rotation at 80. In left rotation, we know that the taller child of 80, which is y, becomes the new root and z becomes the left child of it. And if suppose 85 had any left child, it would have become the right child of 80, right? And then we update the basically height. Now this left rotate will return 85 as a reference. Where it will return? It will return to the basically here, right? So delete node, return 85 as a reference, right? Where it will return? It will return to the delete node 70. It will return here. So 70 dot right is now the reference of 85. So it is connected here. And the tree is balanced also. So height of the 70 is updated and it is balanced. 2 minus 2, 0. Balance of the node 70 is 0. So it is balanced. So this is how the implementation is done for a deletion case. So we saw that rotation logic is same for both deletion and insertion. Only the way we check the imbalance is different. And this we had understood in a detail in our previous videos where we understood the concepts, rotation concepts for delete and insert. This source code, I have updated the link of the source code in the description of the video also, so you can go and check it out. If you like the explanation and the video, please share and subscribe. Thank you so much.